Now, we are interested in getting an expression for L. Therefore, L will be equal to P by 2 by theta by D into R into 1 plus lambda by 2. That is the expression for coefficient of self-inductance of a given solenoid using Raleigh's method. Is that clear to you, sir? Is that clear? The procedure is same. Next we are going to do other applications of this. Same thing we are going to follow. So please, this is a potential detailed question in section C. Please go through this and make notes of this so that I will proceed with the next topic for discussion, sir. My next topic for discussion is calculation of self-inductance of two parallel wires. Calculation of self-inductance of two parallel wires. Calculation of self-inductance two parallel wires. If we draw a diagram for this, let us consider two parallel wires. One is A, the other one is B. This line is the axis of this wire, and the wire is considered to be cylindrical in shape of very small radius when compared to its length. Let us suppose the current is flowing in this direction in these two wires. So we consider this circuit, which consists of two wires A and B, identical to each other. They are placed parallel to each other, and let us say they are separated by a distance d. Is that okay to you, sir? Is that okay to you, sir? The radius of these wires, let me say, the radius of this wire is A. Here is the radius of the wire. Let me repeat once again. We are considering two parallel wires separated by distance d. The direction of current flowing in these wires is indicated with the arrow mark. A be the radius of this wire. Now, from this wire, let us consider some point here which is at a distance x from the wire B. I have taken a point. You can see this point. and this point is at a distance x from the wire B. When current flows, definitely it will produce a magnetic field. So I will write the magnetic field at a distance x from wire B. This is equal to mu naught I by 2 pi x. Mu naught I by 2 pi x, where mu naught is permeability of free space, I is the current flowing to the wire, x is the distance of the point from the axis of wire B. When current is flowing through A, it will also produce a magnetic field at the point B, at this point. Therefore, the magnetic field at the same point due to wire A. This distance is x. The entire distance is d. Therefore, from this wire, this point will be at a distance d minus x. And therefore, I will write this as magnetic field as mu naught I by 2 pi d minus x. So if I add, I will get the total magnetic field. Total magnetic field B will be equal to mu naught I by 2 pi is a common, I will take it out. 2 pi, then I will get 1 by x plus 1 by d minus x. This will be the magnetic field. Is that okay to you, sir? Is that okay to you, sir? Now, what I am going to do is, let me take a small area here of unit length. Please note, I am taking a small, imagine I am taking a small portion here, small area here, whose width is dx, length is unity. I repeat once again, at that point, I have taken a very, very small imaginary portion whose width is dx, length is unity, and the flux due to this magnetic field, let us say, is passing through this area. Is that okay to you? Flux is passing through this area. Then we will write flux through the elementary area of width dx and length unity. This I will write as d phi. Flux I know is magnetic field into area. Magnetic field is B, area is length into breadth, dx into unit length. Therefore, I will write this as d phi is equal to mu naught I by 2 pi into 1 by x plus 1 by d minus x into x. This gives me the magnetic flux. I have to find out what is the total flux. Therefore, total flux phi is equal to integral of d phi. This is equal to mu naught I by 2 pi integral 1 by x plus 1 by d minus x into dx. that okay to you, sir? So if I integrate this, I will get mu naught I by 2 pi 1 by x log x. If I express it in terms of log to the base 10, I have to multiply by 303. Instead, I will write log x. So I need not multiply by 2.3. I am directly taking log. Minus ln, if I integrate this, d minus x. Okay. Now I have to apply limit, because from this point to this point I have to take. Supposing I take this reference as x is equal to 0. Okay. This will be x is equal to a. Okay. Is that okay to you? Then what will be this distance equal to? Okay. Listen to me carefully. If I take this as x is equal to 0, this blue line, dotted line, this will be x is equal to a. Okay. And from here to here it is d, which means from this point to this point, it will be d minus a. Am I right? Am I right? Therefore, I repeat once again, I have taken this axis as x is equal to 0. I already told you the area of this, the radius of this wire is a. Therefore, this is x is equal to a. X is equal to a. From here to here it is d. From here to here it must be d minus a. Is that okay to you? Therefore, I am integrating this expression between the limits a and d minus a. Therefore, I get this as mu naught I by 2 pi. If I apply upper limit d minus a, if I apply lower limit a, therefore log a minus log b can as well be written as log a by b. Therefore, I write it as ln d minus a by a minus ln a by d minus a. Is that okay to you, sir? Is that okay to you, sir? Now, this can be written as mu naught I by 2 pi ln d minus a by a. In order to make it d minus a, I have to become this inverse this. Therefore, it will become plus ln d minus a by a. So I have got the flux phi. Is that okay to you? Is that okay to you, sir? Is that okay to you? Shall I rub this off, this part? Now if I add that, I will be getting it as phi is equal to 2 times mu naught I by 2 pi into ln d minus a by. This is the flux I have got. Now from my previous class, I know flux, coefficient of self-inductance and current can be related like this. Phi is equal to Li. Comparing these two equations, I can as well write comparing the above equations. Okay? Comparing the above equations, I can write this as L is equal to mu naught I by pi ln d minus a by a. That will give me the coefficient of self-inductance of two parallel wires. Mu naught is permeability of free space, I is the current, D is the distance between the two wires, A is the radius of the wire. So what we have done is, due to two wires, we found what is the magnetic field, we found what is the flux between the wires, and we equated with this expression phi is equal to Li, compared, and then we have written expression for L. That's how we arrive at the expression for coefficient of self-inductance of two parallel wires. Is that okay to you, sir? If that is okay to you, we move on to the next topic for discussion, which is coefficient of self-inductance of two coaxial cylinders. Shall I rub this off? Shall I rub this off? I will rub this off. Self-inductance of two coaxial cylinders. This is the axis of the cylinder. I will draw it with a different color. Okay. Now there must be another coaxial cylinder. Let me complete this diagram. Okay. You can increase this length so that it looks clear now. Okay. Okay. I will tell you what all it is. Don't worry. Radius of this cylinder is A. The outer one is B. Okay. Let me take a portion here. This one. I call this as A. I call this as B. From this, somewhere here, I am taking a point P. At what distance? Smaller. And this is AB. This is CD. Okay. I will tell you what is exactly. I will rub this offset. So in the figure, I have shown you two cylinders coaxial with one another. The radius of the inner cylinder is A. The radius of the outer cylinder is B. I repeat, let us consider two coaxial cylinders as shown in the figure. Radius of the inner cylinder is A. Radius of the outer cylinder is B. From the axis of the cylinder at a distance R, I have chosen a point P. Let us suppose a current of I amps is flowing through the inner cylinder. I repeat, we consider two cylinders coaxial with one another. Radius of the inner cylinder is A. Radius of the outer cylinder is B. Through the inner cylinder, a current of I amps is flowing from the axis of this cylinder at a distance r, I have chosen a point P. When current flows, definitely there will be a magnetic field at the point P. Therefore, the magnetic field